Okay, let's get started. Hello everyone, I'm Lucian. Today I'm going to talk about why threads can be considered harmful. So you can find the presentation slides and a couple of notes on this link here. The link is also posted in the chat, so you may find it useful throughout the presentation. So this statement with consider harmful kind of was initiated by Dijkstra in the '68 with his famous paper "Go to statement consider harmful." That started the big trend. And there are two things that I want to highlight from his paper, and those are the following. My second remark is that our intellectual powers are geared to master static relations, and our power to visualize processing evolving in time are relatively poorly developed. We'll see how this applies to threading. The second one is, for that reason, we should do, as wise programmers aware of our limitation, our utmost to shorten the conceptual gap between the static program and the dynamic process, to make the correspondence between the program spread out in text space and the process spread out in time as trivial as possible. Okay, so essentially he argues that gotos are bad because they widen this space between the program and the process, between the static part of the program, what you can see up front by looking at the program, and the execution of that program. And there's another piece of important paper, the Bohm-Jakobini theorem, which appeared two years earlier. And they claim that all the programs can be represented with a sequence selection and repetition flow. And moreover, that's also very interesting in this paper, is that they introduce, or they were one of the first to realize that flow diagrams are really helpful in allowing us to visualize and to better understand how the programs work. And those two things were kind of the setting stones for structured programming, but we're not going to talk about structured programs. There's a beautiful talk by Kevlin about that. So if you're interested in that, please go see that presentation. In this talk, we would argue that threads are like gotos. And similar to gotos, they should be considered harmful and they should be banished from our day-to-day life. Reasoning with thread is hard. Probably most of you will know that. And on top of that, what we want to do, and that's actually the majority of this talk, is to try to find a general alternative to thread. So much like Bohm-Jakobini's theorem for threads, to say that, hey, all these concurrency problems can be represented in this way. So this is the agenda for the talk. We'll start with a problem with threads. Then we'll go to a general solution, coordination without synchronization, composability and decomposability. Then we go to an example. And then at the end, if we have time, we're going to quickly skim through some concurrency patterns. The plan is not to insist too much on them, it's just to kind of highlight that there are patterns in there. The talk is going to be a little bit dense, a little bit abstract. I'm going to show a lot of pictures and a lot of ideas on how to approach threading. Is not going to be showing a lot of examples. There are some examples but they're not a lot of code and day-to-day how-tos to deal with that. Okay, so the problem with the threads. Just to be clear, whenever I'm talking about threads, I mean two things, raw threads and synchronization primitives. And I'll just use the term locks instead of synchronization because that's the thing that actually bothers us, the locking part of the synchronization. So mutexes, semaphores, you name it, they're all in there. And the main problems with threads are performance, understandability, thread safety, and composability, right? And it would be somehow easier if you would have those things in there. But you almost always are likely to get it wrong, right? There are just a few experts out there who just can make threading programs work without too much back and forth, without too many issues in terms of safety, in terms of performance, and understandability, and whatever, right? So that's the main thing. And I'm going to try to look at three different aspects related to that. So the first one is the cost of locking, right, in terms of performance. So whenever we say synchronization, that means locks in this model, and that means bottlenecks. And David Butenhoff has this nice quote that I often joked that instead of picking up this just cute acronym, we should have called the basic synchronization object the bottleneck. Right? And David was one of the people who helped creating the POSIX threads. Right? So mutexes prevent threads from executing different parts. So they are bottlenecks, they prevent stuff. And I often argue with people that they say mutexes are not bottlenecks. Yes, they are. Please look at the definition of a bottleneck. They are, right? They halt free movement and progress. That's their intent. They may not be your biggest bottleneck, but they certainly are in there. So the way things are going, people want to have more performance to their single-threaded application. They add threads, and threads require synchronization, and synchronization means bottleneck. That's kind of the problem with the performance, right? You start with performance, and you end up with bottlenecks. And sometimes it's even worse than where we started from. And I'll have one very interesting example of that. And moreover, it's not just one lock. They do not scale. You have chains of locks and you have prolonged pauses because of those. And I remember 6 years ago, something like that, working on an embedded system which should be real time, so every response should be less than 1 second or whatever. And we had something like 12 chained locks. Like one lock was waiting for another lock, was waiting for another lock, which was waiting for another lock, and so on, something like 12 times. I don't remember the exact numbers. And we had prolonged pauses, something like you would wait 2 minutes for something that should happen instantaneously. That's obviously a problem. That's where the locks would drive us to. So I'm not going to insist on that part. That's, I hope, well known to everybody. I'm going to insist on some part that is less known. I often have discussion heated with people about how many threads do we need to add in our application. So let's take this problem. We have two tasks, each of them taking 1 second, and we have only one core available. How can we express this? So we can just put those two tasks one after another, or we can express them in parallel. If you think about it, most of the people will say, of course, we'll create 2 threads, we'll run them in parallel, and they would get faster. They would be done in 1 second. But actually, if you do that, instead of them finishing up here, what it will happen is they will finish in 2+ seconds. So if you put 2 things in parallel on 1 thread, then those things cannot have more than the resources available, cannot run faster than 1 core. So the lifetime of those 2 things will be extended by 2x. Plus, there is also the back and forth that the CPU has to go between those 2 threads, and that is somehow represented by this red area at the end. So instead of getting all done in 1 second, you get in 2+ seconds. And yeah, that's not good, because the alternative would be this. Both of the tasks would be finished in 2 seconds, and one of them would be finishing in 1 second, right? So even if there is no interaction between those 2 threads, even if the scheduler can magically transport itself and all the CPUs and all the cache from one thread to another, you will still have both of the tasks finishing in 2 seconds, while in this case, you would have one finishing earlier, which is arguably better. Let's take an example of this just to make sure that this is clear. So let's read this text. I arranged it vertically. You'll know why. Happy families are all alike. Every unhappy family is unhappy in its own way. And then the text goes by, he vigorously embraced the pillow on the other side and buried his face in it, right? Those are two pieces of text that you can fairly easily read in separation. But let's try to read them in interleaved, something like this. Happily, he families vigorously are embraced, all the alike pillow on every unhappy, right? Make sense what I'm saying? Okay, ready to do that? Go. Okay, hopefully you've done this exercise in your head. Works kind of okay. In my experiments, I can read the individual text in about 3 seconds. So it takes me 3 plus 3 seconds to read them both. But if I read them interleaved as fast as I can, it takes me about 10 seconds to do that. Right? So that's the similar thing that happens on the CPU when you have more threads than actual cores. Let's look at another example. This is slightly easier to imagine. You're doing it frequently. If I were on the stage, I would be walking in front of you, but I can't, so I'll just try to simulate this.
I think your slides might be frozen. There are 2 threads, one core is the slide showing.
Let me try to replay again. Thank you. So sorry all for that. What I was trying to get to this is that if you execute the task serially, then you would get the results much better than if you execute them in parallel. Not only you would get rid of this switching back and forth between threads, you would also get one task completed way ahead of the other. So that's a good thing. The first example is trying to read a vertical text. Happy families are all alike. I already read that. He vigorously embraced the pillow on the other side and buried his face in it. And the thing is to read this interleaved. Are you seeing this now? Okay, great. Now, I want you to do this exercise on yourself after I'm switching this, right? Try to read the text interleaved. So 3, 2, 1, go. Hopefully you've all succeeded to do that. My results show something like, if I read the individual text, I'm getting something like 3 plus 3 seconds. So 3 seconds to read one text, 3 seconds to read another. But if I try to read the interleaved text, I'm getting about 10 seconds, right? I'm constantly context switching between those two things, and that is a painful thing for my brain, similar to how context switching is painful for the CPU. So the other example that I have here is, let's imagine that we have one task equal to one step, right? Regardless of whether you're doing a left step or a right step, one task is one step. And a serial execution of steps is walking. A concurrent execution would be walking with the title X. You're still going to do the same effort, but it's going to take more of your time, right? So it's something like this. If I'm doing one step at a time, I'm just having a normal walk. If I'm just going with my leg tights, it's far harder for me to actually move, right? And you can try that on your own. That's exactly the same thing that happens on the CPU when you have more threads than the CPU can handle. And that leads us to this important conclusion. The number of threads should be roughly equal to the number of cores if you have CPU-intensive tasks, right? And for raw threads, this is very hard to achieve because typically what you would do, you would devise the threads upfront. You would specify exactly how many threads you have, exactly how many threading functions you would need. And at the execution time, you have a completely different, you have a completely unknown set of CPUs, and you have no idea how to match those things together. So you need to allow frameworks to decide how many worker threads they can create for you to have that, right? So that leaves us with composability. In general, with raw threads and locks, one simply cannot compose two programs. And we've seen this in the industry so many times. You have one component that has a lot of locks and put it together with another component that has another set of lock. It may just deadlock or live lock or whatever. Simply you can't know. You have to know the internals of each of these components to actually know that they can be properly composed. And that also tends to lead to performance problems. So one reason for that is you add extra locking in your components to make sure that they don't have improper interleaving, or you have too many threads or too few threads in your components, and as we've seen, you're not matching the number of CPUs that your core have. Okay, why is this important? Because I argue this is one of the few essential things in software engineering. What do we do when we have a complex problem? We divide it, we solve the smaller problems, and then we compose it back again. If threads are not composable, it means we can't properly use the most important tool that we have in software industry to solve this concurrency problem. So the small conclusion to this is that threads and locks are low-level primitives. They are like gotos. We need to banish them for our general programming. We need to hide them below compilers or libraries or frameworks. Okay. A general solution for that. Now we've discussed so far about the problems, but what do we put instead if we just remove raw threads and if we remove locks? So the first thing, I want to insist on the difference between concurrency and parallelism. So concurrency is a design activities is about expressing the possibility of executing multiple things in parallel, and parallelism is about the actual execution. I can design something that have a 1,000 thread concurrency, but I don't have 1,000 threads to execute those in parallel, right? And the simplified way to think about it is concurrency is about design, parallelism is about execution. And we want to focus on the design. We are software engineers, we need to focus on the design part, right? So concurrency is the main focus of our talk. Let's start with a very simple threaded application, like everyone here, we started programming with a simple thing, maybe hello world, whatever. And we typically have multiple parts into that. They all run on the same thread, but those can be broken up. We can break them up into multiple things that are somehow independent, somehow not tied to the other. They kind of encapsulate one single logic. Typically, that's been approached. That's the approach with function, but we will use the same analogy here. And we take one of that piece and we just call it task for the moment. And the definition of the task that we are using is a task is an independent unit of work. And let me break this down. Unit means that it doesn't make sense to divide it further. at least not for this particular application that we are targeting. You can always divide something further, and in different contexts, it has different meanings, but for the application that you're concerned, it doesn't make sense to divide it further. And independent, it means it will only depend on its inputs. And similarly, the outputs are the only ones that can trigger some changes in the follow-up tasks, right? They don't have messy connections between them. So that's very important, this definition of independent unit of work. The easiest way you can encode this in C++ is something like an std function that returns a void and takes no parameter. We needed to take no parameters because we want to move it around. So the typical way you do it is you would bind those parameters in the task whenever you create a task. And if you have something with tasks, then you can represent any single-threaded problem like this code. Doesn't quite make sense, but I'm just trying to make a point here. Like, yes, you can represent single-threaded problems with tasks, and for different functions in here, you can basically represent all single-threaded problems like this. Let's look now to a multi-threaded application in which we have two threads that are executing at the same time. We're just going to consider a very naive one. And the problem with that is we would have a lot of dependencies between those two things, right? So what do? We can't just leave those things in there because those would really lead to bugs, right? Those are race conditions, so we have to somehow arrange stuff. But if we think about tasks, that's the right way to arrange dependencies. And actually, let's be honest, we've been doing that for a long, long time. I bet every one of us did some task planning at a given point in which the team, the manager, the whatever who's doing the planning, just says, these are the tasks that can be done. Those are the dependencies between those tasks. And you can't have too much parallelism in there, right? That brings me back to the famous quote from Brooks: 9 mothers cannot make one baby in a month, right? There's some inherent maximum limit of concurrency in there. So trying to take this analogy further, we can solve multi-threaded problems with tasks, which again are independent unit of work, and that independent means a lot here. You can't put in parallel two tasks that are dependent of each other because those would break. If we do that, then we can represent all the problems with a graph or an extended graph like this. And this is just an example. I'm having some tasks in here. I have some dependencies. I also have some restrictions. For example, this red thing in here tells me that this task cannot be executed in parallel with this task. It can't be executed with this because this is a predecessor, or with this tree, this one and that one, because those are successors, but it can be executed in parallel with any of these, right? So what we have right now is a way to express the concurrency in any application in some way that allows us to see how we can have concurrency in that application. We know what's the maximum parallelism that we can get out of that application, right? And I would argue, and that's a very strong statement, that every program that is running multi-threaded can be, in one way or another, represented by such a graph. And I'll come to that a little bit later. But one thing to notice here is that this is very similar to the flow diagrams that Bohm and Jacopini have put up. We want to take the same process in structuring our concurrent applications. Okay, so if we do that, if we structure our concurrency with dependencies of tasks, then the first realization that we might have is that we don't ever need any locks in here. We represent locks by constraints, either by dependencies or by restrictions like this one, right? There is no need for locks, and that's very, very important. And again, for all this to work, it means that all these tasks need to be an independent unit of work. You can't have, for example, this task and this task have access or write access to the same resource, because that would make them not independent. The tricky part here is that not all the programs are as easy to put in those things. We have static graphs, or we might have dynamic graphs. In static graphs is like, you know all the tasks that you have in your program, you can arrange it into a graph like this one, and it will work out fine. In a dynamic one, if you have dynamic execution, you don't know how many tasks you have, you don't know upfront all the restrictions and all the dependencies between them, it's going to be harder. So we are going to focus more on the dynamic part. The static part, I just consider it, yeah, it's done. You encode it like that, and then you pipe it into a framework that knows how to handle this type of things, and you're done. So let me very quickly sketch a general algorithm. I'm not going to go, there are some details in here, I'm not going to enter those details. You can read more in some articles you can find on the reference page. So the main idea is that you enqueue a task into the global execution pool to pass it to the worker threads whenever that task can be safely executed, whenever you don't have any other tasks that have dependency or restrictions with the task that you're trying to execute, right? So basically you enqueue that task after all the predecessors are done, and if you don't have any active constraints running. That's one key, one part of the story. The other part is what happens when a task is done. And when that task is done, you have to check, okay, now if this task is done, I need to somehow try to enqueue other tasks. So you check for the successors or other constraints that you might have in there. Right? So in other words, a task starts its successor. So that's the general algorithm that you can employ to solve this problem. And just because I'm going to reference that later, I'm going to put it even more clearly here. So there are two key moments in this algorithm. Before the task is started, which is the responsibility somehow of the caller. The caller knows whenever that task is safe or not, or the caller through its concurrent abstractions. And then after the task is finished, which is the responsibility of the callee, I've finished my main work for this task, and now I'm doing something with it. I have two papers published in Overloads that kind of focuses on that idea. And the main theoretical results are that all concurrent algorithms can be represented by such graphs, either static or dynamic. If we are properly using tasks, independent unit of work, then safety is assured. You don't need for any extra locking for it, right? So we kind of got rid of the major problems that we had in a traditional thread and lock world. The second set of findings, which actually appeared in the first article, is that if you're using a greedy algorithm for your task framework, then you can get high efficiency for that. You're guaranteed to execute the maximum amount of tasks that you can have at a given point. Note, this is a greedy algorithm, so it may not be the absolute optimal, but in practice, it tends to work really well. And also, there are some formulas that guarantee us high speedups. And that is basically the formula. And it's basically based on two main assumptions, is that the overhead of the task management, which there is one overhead of task management, can be really small. So that is especially true if your tasks are slightly larger. So don't put addition in a task, because that's going to have a terrible performance. And tasks are independent by design, so you may have multiple parts of application that can create a lot of tasks at the same time. And this is the formula, and those are some results. So the speed up is greater than n over k plus n minus k over p, where n is the number of tasks that you have in your pool to execute, k is the latency. If you have this assumption that you're looking for a high throughput system, then you can pretty much arrange your problem so that your latency is actually one task. So the speed up for 1,000 threads is 500.25, which is a pretty big one. And for 10 threads is 9.91. Compared to other types of program that I've seen, these are pretty good. Just one very important observation. This completely ignores any indirect contention between the tasks. You always have that, no matter what you're doing, right? So if you're having a hyperthreading processor between two threads, there's always some contention. They don't have full resources to handle that. And even the memory is a bottleneck. You can't access from all the threads the memory at the same time with the same throughput. So beware of indirect contention. It's all over the place. Okay, so coordination without synchronization. So far, we kind of discussed the high-level theory. We kind of discussed how to create tasks, but people are still looking into, have a very lock-oriented mentality. Can do a lot of stuff, but at some point, I'm having some contention of my resource. What do I do about that? And there are nice concurrency abstractions that we can build for those. So let's take the first example. A simple mutex. How would we replace a simple mutex in a task world? So the classic example, we would have two threads. I'm coloring here with magenta with diamonds the part where we are holding the lock, and with red the parts in which we are waiting for the locks, right? And of course the red zones are really bad, and everything else is not contending, so we are fine. How would we represent this type of problem in a task world? We can represent it like that, but that's not good enough. Yes, it works, but it doesn't achieve the best performance. What happens if this task can be executed up here in front of that one? Just have to wait, so you're not maximizing your potential. And moreover, you would have to have a lot of these dependencies, depending on how many tasks you have. Another slightly better solution is you put restrictions. You say something like, this can never be run in parallel with this, or this cannot be run in parallel with that. But that again is not very good, because you don't know how many tasks you have, so you kind of end up in the same place, which it's hard for you to put all those constraints. And it's hard for you to represent this wrong. To better represent this, what I'm trying to do is kind of have a color-coded restrictions. And I'm putting some color-coded thing below a task, indicating like this particular task that I'm having here cannot be run in parallel with anything that's magenta with diamonds in there, right? This can be freely run in parallel with anything else, but this one has some restrictions on top of that, right? This is the same thing as I said, but in words. So a task with restriction cannot run in parallel with a task color like the restriction. And if we have that, then our representation of the problem can look something like this, right? Every of these magenta tasks have an indicator telling that there are some constraints. You cannot simply run all of them in parallel. And you can create how many of these tasks. You don't have that problem of trying to put too many constraints into that. Right, so this is kind of the very high level picture. I'm going to quickly jump to an example to how would you implement this to kind of see this in practice to better visualize this. We would have something like a concurrent abstraction. I call it serializer because it serializes stuff. And whenever you want to do something, in my case, I have a global resource, my backup engine, which just want to back up something, I want to save some data. Instead of just creating tasks and say, hey, backup engine, run this, because this is a global resources and it's not properly independent, I need to put it through a serializer. So the way I'm doing that is I'm saying, my serializer execute this task. So it's almost as easy as enqueuing the task. It's just I need to put it into a serializer instead of the global executor. And this is kind of the high-level picture in which that kind of explains this flow. And I'm trying to read it from the right part to the left part. So we have a number of worker threads. So those are hidden inside the library. They typically correspond to one CPU. Then we have one global executor, which is an executor. So it can execute tasks, but it can execute a lot of tasks at the same time. So if you pass it 4 different tasks, you will try to execute all of those in parallel, provided that you have enough workers, right? But we can build another concurrent abstraction, that is the task serializer, that again can take multiple inputs at the same time. But instead of trying to execute them all in parallel, it will send to the global executor maximum 1 task at a time. What does it do with the rest of the tasks? Well, it just queues them, right? And whenever this task that was sent is done, remember that callee part, whenever the task is done, then you take another task and push it through the global executor. So that's kind of the global scheme in which you're doing that. I realize this is somehow a high-level description of that. I'm not going to go into a lot of details. You can find more details in the papers I've mentioned. But that's the general idea, right? You keep a queue of the tasks that need to be in queue. You keep track of whether you're executing or not a task, not how many tasks, just whether you're executing or not. And then whenever you're finishing executing a task, you try to enqueue the next task. That's the general idea. And it's not hard to implement that. You have to be a little bit careful about the inner details of that with atomics and so on, but it's a pretty straightforward implementation. If we have that, then the way we would solve these types of problem is whenever we have non-constrained tasks, we just pass it to the global executor, and whenever we have something that we have to protect, it accesses a global resource, we pass to a task serializer. And with that, we kind of discuss about 2 types of tasks executor: the global executor that executes a task whenever a worker is free, and a task serializer that executes at most 1 task at a given time. Please know that a task serializer is also an executor. It knows how to execute tasks in a set of constraints, right? And this is not accidental here. I'm using the words executors because they map really well with hopefully the C++23 standard. Okay, another fairly used primitive is read-write mutexes. How would we represent this type of problem? A read-write mutex has two types of zones: the write zone, which is similar to a regular mutex. You can't execute more of these, more than one of these things, and you have also read zones that you can execute them in parallel. So the green with circle things you can execute in parallel, but you can't execute any magenta with another magenta or a magenta with a green one. We would use the same notation, but just note that we are encoding two colors in here. So the magenta with the diamonds and the green with the circles. So single color restrictions or dual color restrictions or n color restrictions, however you like, it's the same. And with that, we can also represent the problem with tasks. So you see the pattern, right? So everything that we could have reproduced with, could have been represented by mutexes, we can represent them with an appropriate notation with tasks. So in this case, the green things are not allowed to run concurrently with the magenta ones. The magenta ones are not allowed to run concurrently with the magenta and the green things. This is an example. It still refers to the backup engines, but let's say we want to add another operation to it that just gets some information and then calls a callback whenever that we get that information out of it. And we can query the backup from multiple threads. That's a safe operation, but we can't query while we are writing to that backup. So it's exactly the same. We have a serializer. In this case is an AW serializer. We have a reader for it, and then we execute some task that just gets the data and then shoves it into the callback and just calls the callback. And I haven't shown here the writer part, but it's similar. In terms of implementation, it is very similar to the one with the serializer. We just have the same workers, the global executor, but in here we need to keep two queues, the read queue and the write queue. And of course, the rules here are slightly different. We can have maximum one write task at a time when we have multiple read tasks at a time, provided that we don't have any write tasks, right? So that's kind of how it works. Again, I'm not stepping into implementation details. And we just grown a little bit the number of executors that we might have. So you see the pattern, we are just adding new and new concurrent abstractions on top of what we have. And actually, by the way, those are two executors in here. So you, for one read-write task serializer, you would have a reader and a writer that are interrelated. Next problem we want to solve, semaphores. Those are also pretty used in industry. So a semaphore is like a mutex, but it has a different count, right? At least I'm taking this approach of semaphore. There are multiple ways in which you can look at semaphores. So in this case, I have a semaphore of count 2. I can execute 2 magenta tasks in parallel, but when I try to start a third one, I'm just going to be blocked. That's a traditional representation of semaphores. To put it into tasks, we have to slightly improve the notation. Besides the color constraint, we also have a max parallel count in here, telling us how many of these can run in parallel. And the problem can be represented, as you guessed, like this. You have all these tasks colored with magenta, and they cannot run in parallel with the magenta with the count of 2. So you can maximally have 2 of those run in parallel. The third one will have to not execute at the same time, not wait. It will not block, but it will not be executed at the same time. I'm going to get back to this in a bit. So I'm going to take my backup example into a slightly different direction. Let's say that a backup can be really slow and you have to do a lot of them. So what do? You create 10 backup engines, and you would want to have maximum 10 of those in parallel. So you create an N serializer. So this is our corresponding abstraction for a semaphore. You initialize it with 10. So 10 is the maximum number of tasks that you can run. You have a concurrent queue of backup engines, and you need to put at least 10 of backup engines into that. And then at the execution time is just exactly the way you have a serializer dot execute, or you can use the C++ 23 notation execute of serializer and the task. And that task in this example is slightly more complex because we are dealing with multiple things. It just pops one engine out of my concurrent queue, then it does the saving part and then pushes back the engine in there, right? So I start with 10 free engines in my queue. While I'm trying to do work with them, I'm extracting them from my queue, and then once I've finished the work with them, I'm just pushing them back in there. Right? I'm assuming no exceptions here, otherwise the example would be somehow more complicated. And just like the case of a normal serializer, it's exactly the same structure. You have a queue of tasks, but here you pass maximum n tasks at a time. And the implementation goes along with a very similar pattern, just slight variations of how many tasks you can put in there. And those are the task executors that we've built so far. Global executor, task executor, read, write, task serial. Global executor, task serializer, read, write, task serializer, and task serializer, right? And for any type of things, you can think of more like latches. You want to put latches in there. Yes, you can build an abstraction for latches. Yes, you can build an abstraction for barriers. So any type of synchronization that you would have in a typical world, you can translate it into a task world. So you can have that type of coordination. So the results so far with this that we obtain in this section. So we have now a systematic way to raise the abstraction. We're not dealing with threads anymore. We're not dealing with synchronization primitive. You can build your own synchronization primitive on top of tasks just by knowing those two things. When it's safe to include a task, and what do you do after the task is finished executing. You don't need any locks. If you do that, all the locks just disappear. And guess what? The threads do not need to block anymore. If you have work to do, then yes, you can maximize the throughput. The tricky part in maximizing the throughput is you have to make sure you have enough tasks in your system. If you don't have enough tasks in your system, then tough luck, right? If you have 2 tasks on a 16 cores machine, your maximum parallelism is going to be 2. But if you make sure that you have more tasks in your system than the number of cores that you have, then you can pretty much keep your CPUs busy and maximize the throughput. And just to be very, very clear, there's a big distinction between locks and serializer. Locks can block threads. Serializer do not block in any circumstances. They may be implemented with some lockless schemes, and different implementation may choose to use some sort of locks here and there. But as a general thing, they do not block, right? The locks, as a consequence, reduce the throughput of the application, right? If you have 8 threads and seven of them are blocked, then guess what? Your throughput is 1/8 of the maximum throughput that you can have. But with serializer, the throughput is okay if you have enough tasks. So even if you serialize a lot of your things through one serializer, but you have other parts of your system that keep generate tasks, then your throughput, your overall throughput for the application would be okay. Okay, hopefully that makes sense. I'm not sure. I haven't followed the chat in here. I'll try to take the answers at the end. There's a lot of material, and I want to make sure that I cover most of it. So the other thing which is extremely important, how do we do composability and decomposability with tasks? Task systems are composable, at least so I thought before hearing Kevlin's keynote on Friday. Apparently, 2S programs are not as composable as one might think. In the context of threading, yes, task system can be composable because the inner constraints are kept. So if you have one component that has a lot of inner constraints in there and you put another component into it, those inner constraints are still kept. If you have tasks from one component that interact with tasks from another component, that's, by the way, a bad design thing. You should try to make all your tasks local. But if you have that, then you may need some extra constraint between those things. But that's the regular process that we do with any type of software, like function. If you want to compose to functions and the APIs don't quite match, you have to write a little bit of wrapper around here and there, right? So there's not something really important in there. I do see I have a question here, so I'll try to answer it before I move too far. But we didn't get rid of the locks, right? They are only now implicit in the task system instead of explicit in your code, but they are still there. Now, instead of 7 thread blocking and 1 executed, we have 7 task scheduler and waiting for 1 task to finish. That is not quite true. So you can build task schedulers without any locks. You can build them completely lockless. The problems that you have multiple workers trying to somehow wait for one task, which never happens, by the way, is not a problem of the task system itself. It's a problem that you don't have enough other tasks. So if you put other tasks in there, if you increase the concurrency of your application, then none of those tasks will, none of those worker thread will be blocked, right? So locks do really block. Task system do not block. They just might have smaller throughput if you don't put enough tasks into them, right? And that's the tricky part, and that depends on every problem. How do you generate that you have enough tasks in your system? Okay, let's move on. Composition is easy. Decomposing tasks is slightly harder. And by decomposing, I mean the following thing. You start with one big problem that you want to solve, and then you decompose it into smaller tasks, and then you try to solve those smaller things. And we typically have that in regular software, right? You can have a function that just calls to other functions. So that's a very simple form of decomposition in there. How do we do that with tasks? If you have a high-level concurrency abstraction, how do you break part of it and use other smaller concurrency abstractions into that? So I'm going to take a running example here. We'll try to decompose task serializer because we just talked about task serializer. And let's assume we have an application that has some multiple types of user accounts, and they all need to be serialized. And one of the tasks is pretty large, and we want to decompose it. So that may be something like what you would have. Change username, change password, profile activity, notification settings. And one task is far bigger than the other. It has to do a lot of queries to get back the result. And this big task is not okay because it's slowing down everything. And you would want to replace that one big thing with a somehow better better concurrency abstraction in there that just has three things in parallel, has some starting code in here, then these three things in parallel, query access, query transactions, query tickets, and then joins the results, and then you're free to move to the next task in your series. How do you do that? That's the big question that we want to solve. And before solving that, I want to go back to the part when I discussed tasks that I said it's important, right? So you have a task, and typically a task is something that does some task work. But I said there are two important parts of that task. Is how do you start the task? So the starting of the task is important. And then what do you do when the task is end? And I'm going to call that from now on continuation. So continuation is the thing that enables the follow-up tasks to be executed. And for now, we're going to just focus on this continuation. If we talk about tasks with continuation, then we would have to revisit slightly how our task looks like. And one simple way in which you can encode a task is a pair of functions in which you have one for the work and one for the continuation. In real life, it's a little bit more complex. You have to deal with exceptions for the continuations and so on. But let's just ignore all that for now. We can represent the serializers as tasks with continuation. Actually, the serializer should be implemented like tasks with continuation. You don't care what the work item is in your task, you care about the continuation. The continuation makes the serializer work. It just starts the next thing to work, right? So the serializer abstraction relies on these continuations to proper work. And in our traditional way of thinking, the continuation is something that is called immediately after the work of the task is done. Okay, if we have that, how do we replace a bigger task that is enqueued into the serializer? How do we replace it with something that executes faster? And there are three steps for doing that. The first step is we exchange the continuation. We put the continuation of this serializer task, we put it at the end of our structure, and we put that continuation that was here, we put it in here. Typically, this is an empty continuation. It doesn't do anything because at the end of that, you don't have anything to do. The second thing you do is, of course, you have to call the new logic, right? At this point in your task, you have to say somehow invoke this logic. And very obviously, you have to remove the old logic. If you've done those three things, then basically you replaced that long task with a different structure of tasks without the serializer even knowing about that. Right? So I just said the serializer only knows about this continuation point over here. It doesn't know what led to this this continuation point. It can be one task, it can be 1,000 tasks, whatever. Right? As long as that continuation is called, the serializer can go on. I realize this is a little bit abstract. I'm switching now to the code. Hopefully that makes things a little bit easier to approach. So I'm having this profile activity function, which is the one that's called by the serializer, right? So from the serializer perspective, from the caller of the serializer, there is no division, there is no decomposition in here, right? I'm calling a function, and that would just be included in the serializer, it get executed, and then other tasks will be executed whenever this one is finished. What I'm doing in this profile activity, the first step, I said I'm going to exchange continuation. I'm going to set an empty continuation here, that's the default parameter, and get the current continuation of the current task. So this is the continuation of the current task. Then I call the new logic. And then what's impossible to show here, I've removed the old logic from here. And let's quickly go over what this new logic does. So I'm creating a last task, which does some aggregate results. So this is the work. And then I pass it here. This is the group, it's not important at this point. I'm passing here the continuation. So whenever this task finish executing, it will call this continuation. Now, this task can be further decomposed, and we have the same thing, but it doesn't matter. This continuation will be called whenever this thing is, at some point, if this task is executed. I'm having this small abstraction here. It's a little bit raw. I could have done it with continuation, but it doesn't matter. It's a finished task that just waits for 3 other tasks. I'm spawning three tasks over here that do some work. And at the end of that work, I'm just saying like, hey, event, notify that I'm done. And after 3 calls of this function, see these 3 over here, this finished task is executed, which will trigger this task and aggregate the results. And at the end of the aggregation of the results, the continuation will pass and the serializer will be executed. Don't expect everyone to fully understand this. It requires a little bit of practice to get used to this code. I just want to point out that this is not something that's complicated and not something that is hard to write, and it's not something that poses threading safety. Yes, you have to take care of several things, like you always have to call the continuation, you have to treat the exceptions, and so on and so forth. But essentially, it's a simple thing, right? Once you get used into this mindset of I'm going to use tasks for the whole thing, everything becomes simple to implement. Hopefully that makes sense for you. The big takeaway for this decomposition is that at this point, we can approach concurrency from a top-down, in a top-down manner, right? Previously, we would start from bottom-up. We would start with threads, we start with locks, and just work our way up. Put 2 things together, those would break, fix those, get back, rewrite parts of component A, rewrite parts of component B, put them together, fix some more issues, then yeah, it works. And then you just go from bottom to top. With this type of decomposition, you can go from top to bottom. And what I would argue is that this is the proper way of designing software. And with this task-based approach, we finally have something. I'm not saying that there aren't other alternatives, there are, but compared to raw threads, we have a good way to approach the problem systematically from top to down and design it properly upfront, design for concurrency and not figure out parallelism problems later. Okay, an example. So I'm going to use the H264 DEC program. It's a video decompression software that's part of StarBench Parallel Benchmark Suite, something you can find online. I've included in my reference for the talk. The basic flow is something like this. You have a lot of frames that you need to decode, and for each frame you pass the frame, you decode the slice entropy, you decode the macro blocks, which typically happens line by line or even more divided, and then you output the frame, right? So you have some kind of a pipeline with this thing being the heaviest task, and that can be further decomposed. The concurrency constraints are pretty much like almost a full pipeline. Stages need to be processed in order for a frame. Parsing needs to be in order. Decode macro block needs to be in order. Line depends on the previous line. Frame output needs to be in order, right? So almost a full pipeline. And the actual benchmark includes a pthread solution, right? So this is the benchmark. I haven't changed anything. This is how it looks like. It has a number of threads. You have one dedicated parser threads. You have n threads for entropy and macro blocks. You have one recorder thread, and you have one output thread. And you would notice that the main majority of work is done on these n threads. That's where the heart of the problem is. The thing that's very interesting here, besides the complication that you have to manage all this, is that you need a special reorder thread. Remember, in the problem description, I never mentioned anything about reordering. If you look at the serial execution, there is no reordering in there. It doesn't need to be a reorder there, but because you've chosen this way of handling the threads, you have to work around, you have to change the design of your solution to add that thing in there. So threading makes the problem much harder to follow. Because of this, and trust me, if you look at the code for that, it's really hard to follow. What I thought it was funny, the interframe dependency, they have a busy wait in the previous macro block. So it's just, if your previous line is not finished, what do you do on your current thread? You busy wait in there. You have a while with no instruction until that's done. So you can see how the performance of that goes in this slide, right? So while you have enough CPUs to throw at this, it works okay. But once you don't, it just falls off the roof, right? And this is the thing that I mentioned with the bottlenecks, right? So we have a bottleneck that if we throw too many threads to this problem, it's actually much worse than if we would just have things running on one single thread. Not to mention the CPU, the energy consumption of all those threads going. And just by the shape of this graph, you can imagine the configuration of my computer. I've done this test, so I have 6 real cores and 12 if you count hyperthreading, right? And you can clearly see in here. And by the way, this gray thing is the ideal execution. So actually, the pre-thread solution is kind of okay for the type of thing that it does. I'm going to try to re-implement the same problem with us. I'm going to use the Concord library. You've seen it in my previous example. This is a library that I try to build to make sense of all this concurrency world, to try to see, experiment with different things and try to see how can we build a general solution. So the general approach is that we would have a pipeline for the general flow, and then we have a task for macro blocks lines, and actually I have multiple tasks for a line. The pipeline looks like this, right? So you see, this is the missing link that I keep mentioning about. It's almost a full pipeline. You just don't have to ordering constraint between the entropy phase. You don't care too much about that because this macro block part is the one that takes the vast majority of time. So there are very few chances in which you can actually execute 2 of those in parallel. But that's the pipeline. That's how you will implement this in Concord. You have a pipeline in here. You say the process, and you say this is the maximum number of maximum concurrency that's allowed for these things. Thread is the parameter that was called in the benchmark. It's not my naming. And then you just add stages, just passing in functions in here. Once you add the stages, you push the first frame. There's a little bit of complication here. You don't know how many frames there are at the beginning, so while you're parsing, you're checking whether there are frames or not. And if there are frames, you push more through your pipeline. So that's why I'm passing the process in the first stage. And also another thing that I'm doing, I'm creating a task group that's just passed to this pipeline. And the main thread does a form of busy waiting for to ensure that all this is executed and then continues afterward. This is not similar to lock waiting and is not similar to busy waiting for that's typically done with atomics. It's just while this group has tasks, I'm going to pick a task and execute it. So I'm trying to be as useful as possible while there's nothing for me to do. That's kind of the general idea here. So no, this is not at all like locks. And for the other problem, so we solve the pipeline thing. This is how you solve it. That's the complete code to solve the pipeline problem, right? There's no more code for that. Except I'm not showing here the data structures. The data structures are needed. The second problem is macro block dependencies. The way the problem is formulated is that when you decode a macro block, it depends on the previous ones, right? So you have some constraints in there. What I do here, I'm trying to group this into multiple blocks at a given time, and I'm basically inventing my a new concurrency abstractions just for processing this matrix. I imagine this can be pretty useful in other domains. So at some point, maybe we just want to say, yeah, this is pretty useful. We stick it into a library. And this process matrix thing just receives a function that takes the x and y. It doesn't know what it processes, just tries to process a matrix. And then whenever it starts with a width and height and a function and a done task, this is called whenever the thing is done. It initializes a bunch of internal members. The trickier part is I'm using here an array of atomics. That may be scary for certain people, but don't worry, there are people who are doing these abstractions, so if you're not into those type of things, you can always find some abstractions ready for you, or that's the hope, at least. And then you just create the first task and then spawn. You start executing from the beginning. And then what this thing does is I'm having a function which just calls the function that I was received as a parameter. And then I have a continuation and returns a task with this function and this continuation. What does the continuation do? Depending on your position on the grid, it tries to unblock either the bottom task or the right task, or both of them. There are cases in which you need to unblock both of them. And then at the end, when you finish everything, then you just have to start the done task saying like, hey, announce yourself, I'm done. Right? And the unblock cells is just checks the ref count. You decreases it when there are no predecessors, then you can freely spawn these things up. So except the member variables, that's the whole pipeline thing, and that's how you process that thing concurrently. Maybe it's useful for other problems as well. I don't know. And we have those two things. How do we put them together? How do we do that decomposition that we mentioned about? And that's how we do it. This is the function that you've seen in my previous slide, stage decode slice MB. It has something that is done at the beginning that's not important. That's present also in the serial algorithm. You take the current continuation of your task. You create an end task with that. You also need to take the group, because we are waiting on the group. So you have to ensure that you're not just finishing up or executing everything in your group. That's a slightly tricky thing you have to do in here. There's your chunk func. This is what you do for each of the macro block in there. And then for that process matrix, you just started with these parameters. And notice here I'm using, I'm not creating one task for each macro block, I'm using one task for each chunk size, which in my example I did some very simple test. The right number was 5. It can depend. With that, we have everything that we need, and we can just put it up to a test. And the green part is the part that's shown by this Concur implementation, and you can see that is slightly better than the pthread solution. In the beginning, it's a little bit worse because the pthread solution has more thread and we have a little bit more constraints in how we've done it, but it's surprisingly efficient. It's surprisingly close to the ideal thing. And it's not the maximum that we could have done. Actually, the pthread solution did something that we didn't do. I haven't explained that in the decoder, you also have dependencies on the previous frame. So you can theoretically start part of the next frame while you're still working on your current frame, doing the macro block decoding. I haven't bothered with that. I just said, let's try a simple approach, right? And even with that simple approach, the performance is pretty good. If you want more performance, what you can do is try to unlock more concurrency, as I said. So the thing that you can do multiple macro block frames at the same time, that's one way to do it. It just complicates a little bit, and it would have been harder for me to explain in this talk. And there's also one thing to notice here is that we have pretty small tasks. We don't have large tasks. So that means that our threading abstraction is relatively high. It's higher than my typical workload would be. So that would be more than, I don't know, a couple of milliseconds. That would be my ideal size for a task in my own domain. It depends from domain to domain. But about naive concurrency, let's look a little bit more carefully about that. So at the pipeline level, at maximum, we can have 4 tasks executing. Maybe a little bit more with these entropy things, but in practice, it doesn't quite happen. So we have 4 of these executing because we have 4 stages. So there's not a lot of concurrency from the pipeline itself. And there's also not a lot of concurrency from the macro blocks decoding, because you can essentially at maximum just go with one diagonal at a time. When you start doing that, you have one task that you can do in parallel. You're starting this, you can have 2 of these in parallel, then 3, and then so on. Right? So there's not a lot of concurrency that is in there. If I would have had this realization before starting to implement this, I would have said, no way this is going to work. I'm no way going to expect some decent numbers out of this algorithm. And yet, we did obtain some very good performance numbers. We talked about performance, let's talk about lines of code. This is not necessarily the most representative way of looking at it, but the Concord solution it's easier to implement than the pthread solution, not to mention the complexity, right? So basically I've shown you what's everything in here to be done. I haven't shown you the data structures and here and there a little bit of glue code, but that's everything that you need to do. We didn't change the problem domain. We just keep it like that. We just divide it into tasks, right? So that's a very important thing. So what do we got so far? If you think about concurrency abstractions, then you find that it's easier to write your code with that. You can use high-level concurrency abstraction. You don't have to deal with, I'm creating these threads, I'm going to create these types of queue, I'm going to do this manual synchronization, I'm going to do this stupid while loop in there to do a spin blocking there. And it can be very efficient, right? You find the code for this on GitHub. You also find it in my resources materials. Okay, so concurrency patterns. I'm going to very quickly go over that. You can create concurrent work. That's how you do it. This is not very complicated. You can have things like I'm having a task and then I wait for something and then another task is spawned. That's a good example is calling something over HTTP. You make an HTTP call, you have a handler, and then you have some task logic that's very simple, and then your thing is called whenever the response is back. If you have two independent tasks that are running in parallel, you can have joins, and we've seen this in our previous example with notified on. Again, we can have done this better. You can have things like fork join. This is a very interesting pattern. You basically do both a fork and a join, but the trick is you can get the fork and the join to be on the same thread. This is useful when you want to keep your thread stack. Trying to use here a recursive algorithm to basically do a concurrent for each. Beware of this. This can save you in some cases, but beware, it may have pretty bad latency implications. Of course, you can create static task graphs. This is how you do it. You create a lot of tasks, and then you say, hey, T1 depends on T2 and T3. T2 depends on T4 and T5. T4 depends on T7. T3 and T5 depend on T6, and so on and so forth. Then when you start the graph, you just start all this thing over. You have serializer. I've shown examples of those. I'm not going to do it now. And then it gets into the algorithmic part of it. Not necessarily a very good fan of that. Those can be very useful, but those definitely should not be the starting point for your application. So you have some collection of items that you want to process concurrently to get some other things. This is how you would do it in Concur. And by the way, since C++17, you have a way to do that in the standard if you have a proper execution policy and the proper library implementation in there. Concurrent reduce is you have a collection and you want to reduce it to one single thing. You want to aggregate somehow the results. This is how you do it in Concur. There's a reduce function. This is how you do it in the standard C++. And the last algorithm that I'm showing is the concurrent scan. We have a collection of elements, you do a lot of processing, and then you get some transformation. But know that in here, every element depends on all the predecessors. It's a very interesting algorithm because in the concurrent version, it adds more work than actually threads available. So that's how you do it in Concur. That's how you do it in C++ standard. Again, I'm just quickly glancing over them. The biggest point in here that I wanted to show is that for everything that you can think of, do it concurrently, there probably is a good high-level concurrency abstraction. Maybe not yet written, but we can write some of that. So we don't need low-level primitives anymore. Okay, so conclusions. We don't have a lot of time. Coming back to Dijkstra's paper, if we take the first quote from here, it perfectly applies to threading as well, to concurrency as well. If we take the second one, we have to slightly modify it. For that reason, we should do, as wise programmers aware of our limitations, our utmost to shorten the conceptual gap between the static program and the dynamic process, to make the correspondence between the program, according to concurrent design, and the process, execution over multiple threads, as trivial as possible. It's almost as, with these two paragraphs, is almost as Dijkstra was referring to threads, right? So we could have said that this is an early indicator of threads considered harmful. So yes, threads are considered harmful, but we do have an alternative for that. We have a global method that doesn't involve any locking, in which we try to, and we do actually, push the threading primitives down to a framework level in a similar way that structured programming pushed to go to the compiler level or a very specialized library level. We don't have to have threading primitives in our general day-to-day code. We have a systematic way of raising the abstraction level, And that systematic way is composable and decomposable. And from now on, I would hope that you won't find any excuse to use raw threads and locks. I started to pull up a web page to actually try to promote this idea that yes, locks are really, really bad. You should not use them. Threads, raw threads are bad. Try not to use them. Use concurrent abstractions on top of that. With that, thank you very much. And we'll have a very short amount of time for questions. Okay. How well does the next task continuation in the chain wait for multiple previous tasks to complete? The continuation doesn't wait for that. The enqueuing part does that. So each time you try to enqueue something, the abstraction in which you are enqueuing that does the checking whether the preconditions are met. So if you are enqueuing a task into the global executor, then you say, this task has no precondition, this is safely to be executed, right? So you as a caller, you're telling that to the system, this is safe to be executed. If you're enqueuing into a serializer, then the serializer will make that check for you. I received a task, but I have another task in execution. So the serializer, before enqueuing that task, will do the check and just queue the task for you. And whenever the previous task finished, then it takes that task out of the queue and runs it for you. And similarly with other primitives, with other abstractions, the point of the abstraction is to take that burden from you to decide when is the right way to enqueue a task. Just do it according to the idea of the abstraction. Okay. Can we describe it as message passing patterns, solutions for the synchronization primitives? Yes and no. They, if you look at the diagrams, yes, they look very much like message passing, but it's a kind of more specialized way of message passing. So, yeah, the answer is both yes and no. With message passing, you don't have all the guarantees of the task. You don't have the performance guarantees, you don't have the safety guarantees, and you don't have that abstraction to reason. You don't have that way of reasoning whether your task is safe to be executed or not. Okay, I disagree with that characterization. It seems like in one case you blame the system for locking, and in the other you blame the problem for not being parallel enough. Both this can happen the same reason, the resource bottleneck, deciding the blame. Okay, so imagine you have two things. You have one serializer, and then let's say you have a massive concurrent for in another part of your system. You push 7 tasks on your tasks on your serializer, and then you push 1,000 tasks in your massive parallel for. With that thing, if you have only 8 threads, you're going to fully go ahead and always have 8 tasks executed at any time. If you go with locks, it may happen that those 7 tasks that you put with a lock will block 7 of your 8 threads. So even if you have far more potential for concurrency in your system, your threads are still blocked. So you have a big performance problem in that part. Hopefully that answers the question. It seems like we are out of time. I can stay here and answer more questions, or I can move in Remo for more discussions. However you prefer. I'll just stay here until they kick me out. So when they kick me out, I'll try to find a place in Remo and then tell you about it. Is there a way to introduce priority to scheduling with tasks? Is that a bad idea? Yes, there is a way. is not necessarily trivial. I often thought about introducing priority serializer. The problem with that is, sorry, let me back off. It depends on what do you mean by priority. So if you have a fixed set of priorities, then yes, that's typically done at the framework level, so you would have multiple priorities. For example, Concur, I think it has 5 priorities to work with. TBB is another implementation of task-based system. It has 3 priorities, as far as I remember. Yes, you can do that if you have a fixed set of priorities. If you have a dynamic set of priorities, the problem that you run into is you have to evaluate the task, you have to reorder the task based on the priorities. So if you have a lot of queuing of tasks, that thing can take some time. So yes, it's doable, but beware of the cost of doing that. If you can frame your problem into having a fixed set of priorities, that would be much better. But that's a great question. Thank you. How is back pressure achieved? I don't know what you mean by that. Can you please elaborate by posting a comment here while I'm trying to get to the other questions? You have compare SQL one API. No, I haven't done that. At this point, my main concern is not necessarily provide the best library to use. I'm trying to find out what would be the abstractions that we should be thinking in terms of. Not necessarily this is the library that you should use because I've profiled it and it's far better than all the competition. Probably is not the best. Well, it performs really well, but I'm not claiming it's the best. Okay, let's say you have more tasks than Marcin responds with a comment. Let's say you have more tasks than threads or pushing many tasks to a serializer. I assume the queue size is limited. Yes, that's a very, very good question. As always, it depends on how you build your serializers. At this point, my serializer, if I remember correctly, it's been a while since I looked at them, uses a dynamic list for the task because it's easier to do a dynamic list in concurrent settings. And those kind of are bounded by the amount of memory you have. So if you plan to create too many tasks, then yes, that can be a problem, right? You have to consider the fact that if you create millions and millions of tasks, those have to sit somewhere. You don't have enough CPU to process them concurrently. But that's kind of with everything, right? So I don't think that that's a particular problem with the task system in this respect. Similar, like if you create millions and millions of threads, probably is going to be worse than that. But yeah, that's a great question. Thank you. Concur lib available somewhere. Yes, Alessandro posted the answer. It's there. Again, it's not yet reached 1.0 and is not fully mature. Any help I can get on that would be great. Really appreciate it. Thank you. In the case of read-write task serializer, are the write tasks prioritized? This is not something that I wanted to insist in here. Basically, you have 2 ways of doing that. You can either prioritize the read task or you can prioritize the write task. I think in my implementation, I prioritize the write task, but to borrow from C++, it should be library library specific. Anyone can implement it in different ways. You just have to somehow document that and somehow make sure you know the implications of that. Ideally, we should implement both of them. We should implement, actually there are multiple versions. We should implement something that favors writes, we should implement something that favors reads, and we should implement something that tries to maintain some kind of fairness between those 2 things. You'll soon find out it's not a very simple problem. So out of the 3 serializer, the read-write serializer is the most trickier one to implement. But yeah, that's a great question. Thank you. if I have an 8-core system, 8 locked threads, and many threads ready to work, I'd expect that OS will choose to execute those ready to work. What's the gain that in the matter? Okay, that's that's why I've insisted so much on the right number of threads in the beginning of the presentation. Ideally, you should have the number of threads equal to the number of cores, assuming you have CPU-intensive applications, right? If you create too many threads, that will downgrade your performance. And I've measured this in multiple ways with multiple applications. Yes, it will downgrade your performance. So a lot of people are telling me, hey, this OS scheduler can do a much better job than we do. No, it cannot, because it doesn't know all the information that you do. You know far more about the problem domain. You can better represent the structure of your concurrency, and you can make sure that you have at any given point enough tasks to execute, right? So no, the scheduler does not do the best thing. It tries. In certain cases, it does a very good job, an amazing job. But in general, again, I'm trying to look at this problem as a general thing, right? So don't take this literally and go apply to every problem that you have. It might not be the case. But in general, this is how it works. Okay, instead of task priorities, did you consider to pass assume task runtimes, the assume relation? This might help in the task scheduler. Pass assume task runtimes. I assume that you mean that I put inside the task all the relations that it has, and then pass it to the task scheduler. Yes, I considered that several times, but I very easily discard it. The problem with that is it quickly becomes a very hard problem to solve. What should the data structures for the task be in order to represent all the possible constraints that we may have on tasks? It's hard to do that. The closest I can get to that, let me go back with the why it keeps happening like this. Is task graphs. Those are kind of doing this thing that you have. So I have a chain task, which is a wrapper on top of task. It still behaves like a task because you can execute it. And it contains the relations, the dependency relations with other tasks. It does not contain restrictions, however. That's a good idea. Maybe it should contain restrictions. And that's how you somehow carry the dependency of the task. The dependency that you have on your task, you can carry them around. Even with this, it's a little bit tricky. What do you do with these chain task objects? Do you still keep them around after you finish? The current implementation that I have, the tasks are just movable. So if you pass it to a task executor one way or another, you'll move it. So you're not going to hold back the task that you've created. With these ones, you can. So it's a little bit tricky how there are other problems that come into play with that. Hopefully that answers your question. How do you deal with transactions that fail? It's a very good question. In the earliest versions of Concur, I'm talking mainly about Concur, but the main point that I want to get out of this talk is not that Concur is the greatest library you should use, is that there are abstractions that you can use, and no matter what the library you're using, you should use those abstractions. So in the early versions of Concur, I put that burden on the actual tasks itself. So I started with implementing raw threads. So if you have a serializer, then the serializer will create a wrapper over your thread and put a try-catch over of your thing, and make sure that even if you fail, then you get some kind of continuation of this. Recently, I started to introduce C++23 executors into Concur, and I'm starting to migrate to that receiver solution. You should be able to deal with the fact that a task has either been canceled or has been stopped with some kind of error. I hope that's what you mean by transaction that fail.